In this video, we will discuss about columns. So Euler has given a buckling load formula, which is called as Euler's formula for buckling load, which is PE, which is buckling load, is equal to pi square EI minimum divided by L square. Here, this is the load in Newton. E is a Young's modulus. I minimum is a minimum inertia of the cross section of the column. So if we look at the column from the top, so column is a very long member, and this is a cross section of the column. Here we have two axes, ixx and iyy, from which it can buckle. So we have to take minimum, whichever is the minimum, we have to take that minimum cross section. Le is the equivalent length of the column. So we will discuss what is equivalent length. Now this particular formula is not applicable for short column because short column fails in crushing. So if the length of the column is small, then it cannot buckle, right? So it will fail in crushing. So this is not applicable. For that we have different formula which we will discuss. It is called as Rankine's formula. So now if you see here k, which is a gyration, then it will be under root of I minimum divided by cross sectional area of this. So k is under root of I minimum divided by area of the column. Now if we see here, we have four different cases for the columns. So here if you see, there is a both end are hinged. In this particular, both end are fixed. Here one end is fixed, the other end is hinged. Hinged means pin joint. Here one end is free, there is nothing connected, and one end is fixed. So if we see in first particular case here, both ends are hinged and there is a buckling load in this column, then it will buckle like this, because in both direction moment is allowed, means there is no resistance in moment direction. And this particular load can be generated if there is a thermal expansion. If we increase the temperature of this beam, then it will have a buckling load inside it. So this particular problem is asked every alternate year in GATE exam. So here if this load is a buckling load which is due to thermal stresses, then it will expand if we increase the temperature and it will buckle like this. So here equivalent length will be L, because this arc shape, both the ends which are passing from the center line of the column, it is passing through this, which is equal to this column only. So it is passing through the center line at both this point. Now if you see both end fixed, then here we are not allowing it to move, so it will buckle like this, and the equivalent length will be L divided by 2. If one end is hinged, then it is free to rotate in at this location, and it is fixed on the other side. So it will have this shape, which the length which is passing from this point and this point, which will be equal to L divided by root 2. And for one end is free, it will simply buckle like this. And if we connect the same arc and we form a perfect arc, then the length total will be 2 times the L. So this particular shape will be twice the length of the column. So L equivalent will be 2 times the length. Now if we see here, slenderness ratio, which is S Le divided by K, L is equivalent length, and which I have shown here. So this all are equivalent length which is formed by the shape, which is the arc shape, and K is this gyration. So for short column, if we define it, then slenderness ratio if less than 32, then we call it short column, otherwise it is a long column. Now here two terms I have defined. Alpha is a length of fixity coefficient, which is this constant here, 1 by 2, 1 by root 2, and 2. L equal to alpha times L, length of fixity coefficient. And if we write this buckling load formula PE as n pi square EI minimum divided by L square, so L is the length of the column and then n is the coefficient, so n will be end of fixity coefficient. So here we are using Le equivalent, Le is equivalent length, here L simple the length of the column. So here constant comes, which is n, so here n equal to end of fixity coefficient. Now if we see this buckling stress, then buckling stress will be simply buckling load divided by the area of this is the area of the cross section of this column. Now which will be equal to pi square ei divided by s square. S is a slenderness ratio. This is slenderness ratio, slenderness. Now if we substitute here k and s in this formula, then we obtain pi square ei by s square, and if we divide it by area, then we remains with this term only. So this is the buckling stress inside this column. So this is very simple 4 cases you have to remember. We can also set that where the buckling stress will be maximum and minimum, where the buckling load will be maximum minimum for particular length of the column. So if this you see P is proportional to LE square, which is inversely proportional. So here if you see LE is more, then buckling load will be less. So this which is has 2L free end, so it will have less buckling load value, so it can carry less load. Similarly, the least is with this fixed end, so this fixed, both end fixed, will have more. So here you can externally also apply this load by just fixing the column and do not allowing it to move anywhere, and you apply the load. So here in these cases you can apply by thermal load only. So thermal stresses means if we increase the temperature, here if you apply externally, then you have to fix this end so that it does not rotate it. So you have to stick it with or weld it to this particular surface. So this was it for this video. So thank you for watching this video. See you in the next video.